Yeah, so we are looking at let's start with Doo's maximal inequality, which gives you an estimate on probability that the maximum of the submartingale exceeds lambda. An interesting thing is that the index of time over which we are taking the maximum doesn't enter the picture. Only the terminal value mn enters the picture, and that is a major result. And we will see its utilization in a short while. Okay, so and the key parts needed for this are basically the definition of martingale, definition of a stopping time, and the Doo's martingale transform theorem that we did. That if you have a martingale, by transforming it via predictable multipliers, you can only remain martingale. And if submartingale will remain only a submartingale as long as the multipliers are non-negative. Okay, so now I come to another very interesting inequality. To begin with, we are just going to talk about a sequence of real numbers, and you all have studied, and few of us may have taught also about you have a sequence of real numbers. How do we show that it converges to a value? And one of our favorite things could be maybe lim sup and lim inf, and when lim sup equal to lim inf, then yes, it is equal to the limit exists and equal to the lim sup lim inf, right? Now, here is a completely different take on my typos. This is less than equal to. So suppose you have a sequence of number xk, 1 less than equal to k less than equal to n, and a less than b are real numbers. So I am continuing to follow where I am using little x for a value and capital X for a random variable. Okay, so these are real numbers, and a and b are a less than b is a real number. Let Sj and Tj be defined as follows. So these are going to be integers, positive integers, non-negative integers. T0 is 0, and for 1 less than equal to j less than equal to n, we define Sj to be first k above Tj minus 1. So k has to be bigger than equal to j minus 1, and first k after Tj minus 1 such that xk is less than n. So k such that Tj minus 1 less than equal to k less than equal to n, and Tk is less than n. Okay, so first k after that time where it is less than a, and then Tj is the first k after that where it is bigger than b. So here is a graph. Pictorially we catch it much earlier. So these are the points s1, s2, x1, x2, x3 dot dot dot. So the first time you go below a is this point. After that, first time you go above b is this point. After this first time you go below a is this point. First time you go above b after that is this one. First time you go below a is this. Now here you continue to be below a, but you don't separately mark it. Okay, and next is this. So this is our 1 point, this is S1, this is T1, this is S2, this will be T2, this will be S3, this will be T3, this will be S4, and endpoint will be T4. And after that, all of them will be just that endpoint. So you start anywhere. First time you go below A, you mark it as S1. After that, first time you go above B, you mark it as T1. After that first time you go below A, you mark it as S2. After that first time you go above B is this, and so on. And algebraically we define. And if Un is the largest J such that Sj minus 1 is less than A and Tj minus Stj is bigger than B. So each of this is called a upcrossing. The connecting dots is not the upcrossing, but the other one, which is this is an upcrossing. S1 to T1 is upcrossing, S2 to T2 is upcrossing, S3 to T3 is upcrossing. Here crossing has begun but has not ended, because you have not actually crossed. So Un is the number of completed upcrossings. So there will be 3. Okay. So you say that you have an upcrossing if you start somewhere where it is you are below and then you go above B. That is an upcrossing. Next upcrossing you will start next time you go below A, and so on. And Un is the total number of upcrossings up to time n. And clearly for a convergent sequence, number of upcrossings have to be finite for any A strictly less than B. You can say that a sequence is converging in real numbers if and only if number of upcrossings of AB, UNAB, limit over n, UNAB is finite for every A less than B. Trivial to write this as a statement and to prove the statement, almost trivial. What is interesting is that if you
His voice is getting cut.
you end it with a positive sign. So each upcrossing, you take the upper point minus the lower point of that upcrossing over. So this is the summation of upcross. This is the summation of x's, but we are selectively choosing which one to add and which one not to add. Okay, and then of equal to number of upcrossings times B minus A. But there can be, the last one can be an unfinished upcrossing. So we have to account for that, and then a little bit of this we can tell us that it might A. If it is below A, then the endpoint minus A. So the right now in this example, xn minus A is, this is xn, this is A, xn minus A is this, but actually the unfinished upcrossing is actually this xn minus this point. So the unfinished one will only be, negative line will be only less than xn minus A minus. So this sheet itself, this screen itself is telling us a whole lot of information as to what is involved. Okay. So once again, you have a sequence A and xn, then you take a less than B, and then you think about it as follows. Suppose these xn's are some prices of some shares or prices something which are constantly fluctuating. Okay. So you buy some, you are sitting with a pot of money, you don't do anything. As soon as the price goes below A, you buy. After that, whether it goes down or goes up, you sit doing nothing till if it goes above B, you sell. How much money you have made? This minus this. Continue to follow this. Okay. The total money you would win will be this plus this plus this. But last one you have put in some money which is still unfinished, which may not gone above B. So what is the maximum that you can go down? That is this value listed here. So the left hand side is the summation of overall things, your net gain from your strategy. It can be negative, but your net gain from the strategy. and it is bounded above n times the b minus a, and then this one last bit. But really speaking, this has nothing to do with probability. This is something which is simply a thing with analysis. That a sequence is convergent to a real number in R if and only if number of upcrossings un ab limit over n is finite for every a less than b. Now naturally we don't do it in analysis because where will you use it? Anybody can write a theorem, but its usefulness, I mean, it will be noted by others only when you use it. And we'll see that in analysis this may have no use, but in probability it has immense use, and we will be using that now. So I put in this, what I described the strategy that, if you are, it is 1, if you are about, your upcrossing is continuing but has not yet ended, you put it as 1 and 0 otherwise, and the gain will be this. So this also observation I already made, that you have a bounded sequence converges if and only if supremum over n un ab is finite for all a less than b. Now, so this was deterministic. Now let us come to a super martingale mk. Okay. Let us, so now, as I said, I am using capital letters when these are random variables, and now little s and little t I have changed it to sigma tau and sigma j and tau j, and we use the same definitions. So one of them is the start time, one of them is the stop time, but we just, the name initially started with stopping, so therefore it continues to get the name stopping time, but it can be used to start or to stop. So sigma is the starting time, tau is the stopping time. You start investing if you are after sigma j, and when you reach tau j you stop and continue to do that. And un is the total number such that this happens, and then we have the inequality that your net gain from this strategy, which is summation of this, and as we had already written down fk, the net gain summation this is exactly summation fk m1 m2 m1 m2 mk minus 1 mk minus mk minus 1, and that will be greater than equal to this quantity. Now, since we argued that mk is a super martingale, since our assumption was that mk is a super martingale, it follows that the expected value of this object is negative. And if expected is negative, but this whole thing is positive, that means this quantity is also negative. Expected value of this quantity is also negative. And from there, by taking expectations, we'll get that expected upcrossings, expected number of upcrossings is less than equal to expected number of this quantity, mn minus a minus b minus a. So, something which we had already noted, that we can't guarantee that the strategy will give you positive returns, but the net gain of this thing can only will be all positive terms at best. At worst, you will be only the last endpoint is where your analysis may be, or your strategy may be giving you a bad result. And that is what is captured in this estimate here, that the expected value of upcrossings is less than equal to expected value of mn minus a minus b minus a. And what we just now did is proving the third major lemma by Doob that we have. Upcrossings lemma, if the super martingale, if a is less than b, this denotes the number of upcrossings of the interval, then one has expected un is less than equal to expected bn minus a minus b minus a, and this itself can be changed to, and upper bound will be absolute value of mn plus absolute value of a divided by b minus a. So we have Doob's upcrossings lemma or Doob's upcrossings theorem. So maximal inequality and the upcrossings lemma or upcrossings theorem, and the martingale transform. These three major results on martingales, all due to Doob, and perhaps all in an era of about 10 years in the 1950s that Doob made these things popular and wrote his first book, wrote his book called Stochastic Processes. Difficult to read now because of just the notations and terminology used there, but it's a gem of a book. And this set the tone for happenings and research in probability theory for decades to come. Okay. So, to sum up at this point, the three major results that we talked about are the definition of martingales and stop times, then the martingale transforms, the maximal inequality, and the upcrossings inequality or upcrossings lemma, upcrossings theorem. Okay, and the three together are extremely powerful tools, and at least one application of these to give you a major result I'm going to do. The entire probability theory is full of applications of this. I may just add that in my MSc final year or MStat final year, 1977-1978 era, so it's already 45 years ago, Professor B.V. Rao taught us martingales in my final year, and during that, while he was teaching us, we had a big time probabilist called Navu from France visiting us, and there was going to be a research seminar, and Professor B.V. Rao told us that there were only two of us in our class. He told us that you have enough background to attend the research seminar. And so the first seminar I ever attended as a student, while still a master student, was a lecture by Jacques Navu, and the result was that the talk was about on a proof of ergodic theorem in maths using martingale techniques. Okay. So of course it is not as simple as the Weierstrass inequality, which I could write down only on one slide, the proof. The proof is little more complicated. So I have of course not included here, but just to outline to you that, and the basic tools for the three results that we've done now. Now these three can be used in any different ways and get hold of the ergodic theorem. Okay. So which is, you can say, a measure theoretic thing. In measure theory, strictly speaking, it's nothing to do with probability. It's a theorem about transformations and ergodic transformations, what are defined to be. All right. So next, what I am going to do is to show the power of these three tools that we did. Okay. Only thing is that to get the full power, we have to go beyond our countable framework, that the omega itself, the number of things is only finite or countable. We increase it just a little bit more. You need not worry, focus on omega, but if you have a sequence of random variables, all of them are only taking finitely many or countably many. Each xk or mk or whatever we talked about takes only countably many values or finitely many values. Everything we did, all the things that we did, calculations, continue to hold with the same proofs. Now you may wonder why I didn't say it in the beginning. Well, it was to tell you that while we are only, everything is only a complete calculation involving a countable sequence of real numbers. And here a little more technicality will be involved, as we will see. You don't need to go through any very general space. So what I'm going to do is apply this to show how this can give you a proof of Radon-Nikodym theorem on real line, which by itself has nothing to do with probability. And then, but of course you may say that, sir, we already have done Radon-Nikodym theorem, so what is the big deal in doing Radon-Nikodym theorem using martingale techniques? And you will get an answer to that, you get Radon-Nikodym theorem and lot bit more than what Radon and Nikodym had put in their framework. You'll get a lot more than that. All right. So let gamma now be the unit interval, and let D be the Borel sigma field or Borel sigma algebra. So probabilists call it sigma field, and mathematicians who are not into probability will call it sigma algebra. But just a collection of sets which is closed under unions and intersections and countable unions, and has the null set there and closed under complements. That is the basic object on which measures are defined. So nothing more than a measure we are going to use. So no probability, but just measure. And the theorem is that suppose mu and nu are finite measures such that nu is absolutely continuous with respect to mu, namely for all epsilon positive there is a delta such that A belonging to this sigma field or sigma algebra and mu A less than delta implies sigma A less than epsilon. Okay. So absolute continuity, classic definition. I don't know why I was writing something else and I had written this. This may be needed in the next step. I will come to that. Now, let us do the following. Yeah, so without loss of generality, we can assume that mu is 1 and mk means any function on gamma can be viewed as a random variable. Okay, I did some rearrangement of text and therefore this problem has occurred, but I'll fix it in a minute. Okay, so this is the framework. You have a unit interval and you have measures on the Borel field or Borel algebra, Borel sigma algebra, mu and nu. First statement is that because they are finite measures, we can just multiply by a constant and take mu of the entire space to be 1. Once that happens, any function can be thought of as a random. Any real valued function can be thought of as a random variable. In particular, now I am defining a sequence of functions. So let's take this dyadic rationals. For a fixed k, you are dividing the interval into 2 power k many parts, subintervals. Each subinterval I am calling it a sub k. A sub 1, a sub 2, a sub 3, dot dot dot. Okay, and then I define this function to be equal to this formula, and this is where I think that remark that I had written, I think this fit it on a thing, I rearrange the thing. So they are using the convention that a by b equals 0 if b is 0. So in other words, if mu of ak is 0, I take the ratio to be 0, and so therefore it is defined for irrespective. When mu ak is 0, numerator is also 0. That is what our absolute continuity will ensure, that if mu of a set is 0, mu of that set is also 0. So with that convention, this ratio will be defined to be 0. With that, these functions are well defined. So I have divided in the interval, and in each one I am taking the ratios of mu's, mu of that interval divided measure under mu divided by measure under mu ratio, and my function is defined on the entire interval. At any point, you take the interval to which that point belongs and you take this ratio on that point. So my mk is now actually a finite value. Mk takes only values, real values, but finitely many. And so nk can be viewed as a Radon-Nikodym derivative of nu k with respect to mu k. Where mu k and nu k are restrictions of mu and nu to the finite algebra or field generated by this partition. Yeah. So you divide it into 2 power k parts. This gives you a partition of unit interval. The algebra generated by this partition is what is I can denote it by fk, and restrict the measures mu and nu to these fk's. Now they are finite objects. On that, we are in the framework where we started. This is the Radon-Nicodemus derivative. This is the function. This is the random variable. And for any subset B in this subset, mu of B is expected value of mu indicator B, where B is union of some subcollection. Because how do we take this expected value? You will have to take B, whichever AK it belongs, so you have to multiply MK by that indicator, take its measure. That measure will be mu of that set, and you multiply it by the ratio that will give you nu of that set, and then you are adding over all the sets where this point x is there, so that will give you nu of nu. So this is a trivial, notationally complicated looks like, but a trivial calculation that for this finitely many finite valued random variable that this random variable that I defined on this finite probability space involving 2 power k points, okay, our definitions work, and this is exactly the expected value of this random variable. Okay. So my omega is not countable, but my this random variable is actually defined on a finite. It can be thought of as having been defined on a finite set, finite partition. Okay. And if you compare two of them at a time, we can take the larger partition, and both of them together can be seen as defined on that finite partition. Or finitely many, if you take first m1, m2 up to mn, all of them can be thought of as defined on a partition involving 2 power n points. And therefore, all the calculations which we did work for this framework. So here is the observation. The partition AJ1 is a finer than AK1, AK2, AK2, K1. If J, if J is less than K, then this is finer, and therefore AK is contained in AJ. Every point here is a union of some finitely many values here, and therefore we are in good shape, and we can actually show this, that this MKs that we define now are actually a martingale. So let's go to MK plus 1 from MK. What would happen? If you want to compare MK and MK plus 1 at any given point, so you take a point, say here, okay, then when you go to the K plus 1 partitions, what would happen? This interval that we have will get divided into two partitions. Next, our point will be either here or here. So this ratio will be then divided as ratio of this two, ratio of nu over this interval and ratio of nu over that interval. But if you multiply them by mu of AK, mu of this part and this by mu of that part, and take their sum, it will be equal to taking this ratio and multiplying by mu k of the whole interval. So the rate matching will happen, and again it's a fairly simple algebra to verify that this MK so defined satisfies the martingale property, because each MK is taking only finitely many values. One can verify point-wise that it satisfies the martingale property. And then one consequence will be, I already observed that this MK can be thought of as a Radon-Nicodemus derivative of mu with respect to mu on that finite space. So as a consequence, we can take the sequence of observables suitably. It will just tell us what is the index of that point, etc. And nu of mu k, mk bigger than t is just expected value of under mu of this object. This is a computation that our ratio that we defined is working as a Radon-Nikodym derivative on this finite on fields obtained by finite partitions. Okay. So the while we are working with measures on unit interval and the Borel sigma algebra and all that, has all kinds of things there, but tools we are using are only at any given time we are only using finitely many objects at a time. All that we have used earlier is applicable, and we will get that the MKs that we have defined is a martingale. So that is my observation. While the underlying probability space is no longer a countable set, each MK takes only finitely many values, or it works on only a algebra of finitely many generated by finitely many sets, and can be all the discussions regarding martingales as well as the inequality that we deduced continue to be true with the same proof as given earlier. We don't have to rewrite any proof. Now, we already saw that MK is a martingale, and therefore using the computations that we did or the theorem, we will get an estimate on the upcrossings. Number of times our upcrossings of this martingale MK, which are Radon-Nikodym derivatives on these partitions. Okay? The upcrossings of those objects are bounded above by this. Now, MNs are non-negative by our definition, and expectation at any time is 1. We will get that this expected value is less than or equal to 1 plus mod A divided by B minus A. This calculation is using only our finite calculations that finite object calculations that we have done till now. Up to time n, m1, m2, mn, all of them can be viewed as being defined on a set which is has only 2 power n entries. 2 power n entries, and on that we have defined all these objects. From there, we get this calculation. But now we interpret as something which has been defined. UN's upcrossings have been defined on the entire unit interval for every n. Then upcrossings up to time n of this interval A to P is an increasing sequence. And then, therefore, supremum or n UNAB will be less than or equal to E mu. This says that the upcrossings converge. So Duke's upcrossings inequality tells us that the upcrossings obtained via this Radon-Nikodym derivatives obtained on these finite partitions converge pointwise. And for those who work with analysis and proving this, often you want to prove a certain thing converges to something else. Major chunk of work goes in proving that that object converges, and then a little bit more to show that the limiting object is exactly what you have claimed to be. Often the major part of work is in proving convergence, which we already have done. And now, using a few simple things, we can show that the convergence is actually to the required object. So this is another fact from measure theory, which is not stressed much in analysis courses when they do just the minimal measure theory, but is stressed a lot in probability theory sessions, which is the following. There is a notion of uniform integrability of a sequence of functions. I have written here in terms of expected value, but equivalently the same I can write in terms of integral with respect to d nu. Forget expectation, it could be integral mod fn indicator fn bigger than m k d mu. Mu is some measure. Okay. So this function is said to be uniformly integrable with respect to this sequence if you take integral over the set that function bigger than k. Integrability says that this will go to 0 as k goes to infinity. Uniform integrable means you take supremum over n and it still goes to 0. And the fact is that Fn converges almost everywhere to F if and only if this converges to 0. So, sorry. In general, convergence almost everywhere doesn't tell you anything about convergence in L1. You can have examples where all objects are L1, Fn converges to F uniform almost everywhere, but it doesn't converge in L1. The uniform integrability is the gap. If you have uniform almost everywhere convergence and uniform integrability, together you get L1 convergence. Typically, we do this in dominated convergence theorem. So if you have Fn's are dominated, then they are uniformly integrable, but that's only a sufficient condition. Here is a lot more. This is there in analysis books, but not stressed in analysis course. Not all books, but several books it will be there. Called uniform integrability. All probability books is there. All right. So here we can verify uniform integrability by using another tool done by do. So using martingale techniques, we can check that this Mn indicator Mn bigger than k is equal to the integral under nu of indicator Mn bigger than k, which is the measure of Mn bigger than k, and then absolute continuity argument, epsilon delta definition of absolute continuity is going to give us that pick an epsilon, given epsilon, get a delta such that measure less than delta implies new measure is less than epsilon. And now for any k bigger than 1 by delta, mu of Mn bigger than k is less than 1 by k, this which is less than delta. From there we will get that mu is less than epsilon, and therefore we will get that mu of Mn bigger than k is less than epsilon. So this required expectation less than epsilon. So absolute continuity gives us that our Mn's that we constructed. So let's come back to Mn's. This Mn's. So if mu is absolutely continuous with respect to mu, first of all, that this is well defined, that denominator is 0, then the numerator is also 0. And secondly, with respect to mu as a measure space, these functions are uniformly integrable. Both these are simple facts which come from measure theory calculations. And almost everywhere convergence comes from Dub's techniques and results, and together they give us that Fn converges to F in L1. Moreover, the convergence in L1 means we had already checked that this nu b is this for every j bigger than k. So L1 convergence will give us that mu of b is equal to expectation mu m star indicator b for every b in fk. So as long as b is an interval coming out of is a finite union of dyadic rationals of index k, this is true for any k. So as long as it's an interval of any dyadic rationals, mu of b is equal to expectation mu m star indicator b. Then again, recourse to measure theory standard mumbo jumbo will give us that mu b equal to indicator mu. This equation continues to hold over the entire subset B, entire sets B in the sigma field, and therefore it's a Radon-Nikodym derivative. Okay, so coming back, technically the whole thing was to just take these dyadic rationals and take the Radon-Nikodym derivative on this finite field or finite algebra of sets, and that can be defined trivially. And then we have that this martingale techniques are telling us that these objects converge in L1 and almost surely to a vector, to a function, and that function is the Radon-Nikodym derivative or is a version of Radon-Nikodym derivative. Now, so yet another proof is fine, but what is the advantage? being measurable
Your voice is breaking.
thought of as a measurable family of measures. And my voice is breaking, so maybe some problem with my internet, maybe. Is it better now?
Yeah, it's better now, but
Yeah, it's better.
last 2 minutes it was kind of was not audible.
Okay, maybe the distance had gone more. I'll hold it closer to my voice. Okay, so if coming back for a few minutes, if it may be lost, a family of measures, mu s, indexed by s in say 0, 1, and such that s going to nu a is measurable for every interval a or for every Borel set a. Okay. Then the martingale proof given above shows that the Radon-Nicotian derivative m star s can be chosen such that Sx going to m star Sx is jointly measurable. This will be true because our m star Sk, if I call it, the kth object mks, the kth object that we define will be measurable, and then we have constructed explicitly the limiting objects, so they will be measurable. And so this you will get that the Radon-Nicotian derivative on one hand for every s it's a Radon-Nicotian derivative, and as a function of s and x it is jointly measurable. Such techniques or such things become important even in something like harmonic analysis. And when you may have index of measures and you want to do jointly measurable Radon-Nicotian derivative will solve the problem. So this is where the power is coming. By any other proof that you may have seen, joint measurability will be very difficult to get. I can't say that you cannot get, but it will be very difficult to get. Not so easy. Whereas here, primarily tools that we have used are the three primary tools of Duke that we used, and then standard measure theory. You can't exit measure theory because our final result is measure theoretic. But only that much. No additional stuff is needed. Then is the standard measure theory. Additional stuff needed only were notion of martingale, stopping times, martingale transform, maximal inequality, and upcrossings inequality, which we did. I don't say I wrote out proofs completely, but you can check books, and that is easy to do proofs. It can be even a project for master's students. Write down in the finite case, write down proofs of all these things. Okay. More interestingly is that essentially the same techniques can be used to get the very general version from martingales when you move away from finite objects to general martingales, namely defined on arbitrary measure spaces. You are not putting only finite omega. The techniques for these three results are essentially the same. And of course, many tools, many books will have it, but you may have to do a lot of background to reach that chapter where these things will be done. So one way to do it is because this is in chapter 1 of my book with Professor B.V. Rao, Introduction to Stochastic Calculus. This was in 2018. There's also an Indian edition there. Also, online editions are there, and you can trace and you can get hold of online thing. I'm sure all you know how to get online things from the internet. So you can, but it's there also on Hindustan Book Publication. So it may be already in some various libraries also, wherever they get the NBHM books from Hindustan Book. So this is part of the Hindustan Book series, also a Springer series, and this is all in chapter 1. So you don't need much background to even do these three theorems in the more general case. Okay. So any question about Radon-Nicotian, I can talk now. Otherwise, I have one small application also, that is a probability theory application. So I first did it, which is a application going beyond probability. Any question about this? So if not, let me go to the second application that I had written out. So once again, we are talking on the open unit interval, open close. So closed at 0, open at 1 unit interval, and let skx be the kth digit in the dyadic expansion of x. So you just store x as is done in our computer systems as in the dyadic expansions. So you take skx be the dyadic expansion of an integer, okay, of not an integer, of a real number between 0 and 1. Now, intuitively, it is clear that if you know the first k digit, doesn't tell you anything about what the k plus first digit will be. Again, because first k digit will tell you which interval you have gone at one point, but beyond that you don't know anymore. Next one will be 1 or 0, would depend on whether it is the first half or the second half of the interval where you have reached. Okay. So therefore, if you are looking at uniform probability allocation to the unit interval, then the next digit will be 0 and 1 with equal probability. So if you define uk to be instead of 1 and 0, I want to convert it to 1 and minus 1. So if 1 remains 1 but 0 becomes minus 1, so you take 2 times sk minus 1. Now you will get that uk will be each, we already talked about independence, and then we have each of them is 0 and 1 with probability half. So uk will be 1 and minus 1 with probability half. So this becomes a sequence of IID random variables, and each with probability expectation will be 0. So this is called random walk, and there are many writings in probability books called drunkard's walk or random walk. So the description is, there's a person who is dead drunk, he doesn't know what he's doing, so he tosses a coin. If it's head, he goes +1. If it is tail, he goes -1. And then you are analyzing what happens to him eventually. So what is the partial for this?
Your voice is breaking again. Your voice is breaking again.
Okay. Does it improve?
Right now it's good, yeah.
Wonder. So I think it may not be the distance, but it's just the exact location between my iPad and my voice. Okay. All right.
When you started drunkard walk, after that it started breaking.
It would appear as if I am myself drunk. Okay. So this SK is also called drunkard's walk. In other words, a drunkard person who doesn't know what is happening, he tosses a coin. If it is head, he goes +1. If it is minus tail, he goes -1. And so SK is the net location where he would be at the time K. Okay. Or random walk. You are just walking randomly. You don't know where you are going. You, head you go +1, tail you go -1, and you are where you reach. Okay. Sometimes also called symmetric random walk. Very popular in. From here one can get to all kinds of very interesting examples from starting with random walk. So question, what is the long-term behavior of the random walk? Can it happen that, let's say, this fellow or drunkard man or the random walk will keep fluctuating between, let's say, +1000 and -1000 and will never cross that boundary? Or fix an integer a and let PA be the probability that SK will be equal to A for some K bigger than equal to 1. Question, is PA equal to 1? So you go far away, somewhere a billion. What is the probability that at some point you will reach 1 billion? Is this probability 1? More precisely, let's fix one negative number and one positive number, and let QA be the probability that you hit A before you hit -B. What is this QAB? So as we were talking about any finance application or any gambling application, nobody has infinite money in their pocket. You assume that whatever it is some finite number. So how will you reach A before you hit your negative value at which you will be thrown out of the system? So we think about B as a thing. If you reach B, you are going to be thrown out, so you will never reach A. And what is the probability that you will reach A before you hit B? Negative B. Okay. What is that probability? So, and now if you know QAB, from there we can make a judgment about what this PA will be. And what if we get that PA is 1 always, then we have got the long-term behavior of the random walk. So, just by posing these 3 questions, we realize that the QAB, computation of QAB is an important aspect. Once you get hold of that, you are game. You can do other things. Okay? And computation of QAB, likewise, now can reduce it to computations with respect to martingales of finite objects. So, this we already talked about UKs being IID that or being independent. So the expectation of UK plus 1 given U1, U2, UK is 0. And hence SK, which is the partial sums, also satisfies that expected value of SK plus 1 given the first K objects. The total first K objects you already know. The new object you have added as mean 0. So the total has mean 0. Therefore, you are where you were previous time. So this is a martingale. So trivially, the random walk is a martingale, which means 0. Important calculation is squares. So now you take expected value of S square K plus 1. Now S square K plus 1 can be written as S square K plus 2 SK UK plus 1 plus UK plus 1 square. And SK square expected value given conditional because it's a function of U1, U2, UK, it will be SK square. Expected value of this term will be 0 because SK will be a constant once you are given the entire thing up to time K, and expectation of UK plus 1 given the background history will be 0. So expected value of this will be 0. Conditional expectation of this will be 0. And conditional expectation of this is independent of U1, U2, UK. So this will be same as expectation of U square, which will, U square is always 1 in any case. No need to do any expectations. You are either plus 1 or minus 1. So it is 1 always. U square is always 1. So you get S square K plus 1. Therefore, if you define Zk to be S square K minus N, we will see that Zk becomes a martingale. So by some simple transformations, out of our original system, we have got hold of 2 sequence of martingales, Sk and Zk. Okay. Locations and the square of the location in minus N, the time taken. So now let us fix A minus B less than 0 less than A, and let tau A minus B be the first time you hit either a A or a minus B. And our aim will be whether you hit at A or whether you hit at B. Right? So where we use the convention that infimum over an infinite set is 0. And let's see, when will this be equal to infinity? If your Sk never hits A or minus B, it stays inside it is not in minus B and it is not in A, but it is only in the interval between that. So I didn't write it correctly. Maybe either I should write it as an interval minus B to A, or if I write it as a set, then I have to write at minus B plus 1 to A minus 1. So I need to correct this. I will. Alright. So now this is a stop time, and if you take S at tau A minus B minimum N, that means you don't go beyond N if you have not stopped before N. If you are only looking at S1, S2, Sn, you define this stopping time to be this minimum N, that's the stop time, and this will be always in any case less than equal to maximum of A and B. Since Sk and Zn are martingales and these are bounded stop times, it will follow that Sk minimum tau AB and Sk minimum tau AB, A minimum minus B are martingales with mean 0. Now, upcrossings inequality will tell us that Sk converges almost surely, and Sk converging almost surely says that Sk will be equal to Sk plus 1. That will tell us that you have to be either at A or minus B, because anywhere in between, next step you can never be same. You will be either plus 1 or minus 1. So that means almost surely you would have hit A or B. So this is the upcrossings inequality will tell us that you will be hitting A or B with probability 1. And then this is a simple algebra calculation, and mean 0 will tell us that actually the probability of hitting the upper bound is B by A plus B, and probability of hitting the lower bound is A by A plus B. And a little bit with squared, you can go over this calculation later, but it will tell us that the expected value is A times B. The time taken to hit A or minus B, expected value is AB. So from here we get this important conclusions that you are anyway going to hit A, but to get to that, we'll have to take limit as B goes to minus infinity, and then your expectation of this will be infinity. So a drunkard will surely hit any point you want, but the expected value of time taken to hit that point is going to be infinity. You can't put an upper bound on how long it will take to reach that point. Expected value will be infinity. So these are hurried over maybe because of the time limits, but it is written out here. I'll clean it up and also put it up in 2 or 3 days. I will send a cleaned up version to Archana, who will put it in the appropriate location. But we have answers to these 3 questions, and the answers is long-term behavior is you fix any point, eventually you will hit that point, but the time which may elapse before you hit that time may be infinitely large. Expected value can be huge, it can be infinity. PA is 1, QAB we computed, but long time behavior we answered. And all this, apart from some simple mathematical tools, only probabilistic computations we needed came from these 3 basic tools of loop which we covered today. Maximal inequality, upcrossings inequality, and the martingale transforms. These 3 tools. So let me stop here.